So, we are discussing infinite series, then we have seen some test in which we can say that whether the series converges or diverges, mainly the comparison test what we have seen can tell us that comparing with other known series which we know that they are convergent or divergent, we can conclude the given series to be convergent or divergent. And then we discuss the limit comparison test. So, now let us see some basic algebra of infinite series. Now, suppose summation over n equal to 1 to infinity a n and convergent. So, both of them are convergent series. Then summation n equal to 1 to infinity a n plus b n, this is convergent. Then for C belongs to R, summation over n equal to 1 to infinity C of a n convergent. And here observe that we need these two conditions. If we do not have these two conditions, then this may not hold, in the sense that you can take a n to be n and b n to be minus of n. So, a n plus b n, that is 0, that is convergent, but n. So, what if we have two convergent series, then what we can write it down is equal to and summation over a n plus b n, this is equal to summation over a n plus summation over b n. We can split them provided both of them are convergent. Otherwise, as we have just now discussed, if you take a n to be n and b n to be minus of n, then a n plus b n is going to be 0, left hand side is 0, but right hand side is not. This is very important. Whenever you have both the series convergence, then you can play around with them. Proof is essentially the limit laws, because in order to get certain conclusion about the convergent series, you need to consider the partial nth partial sum, and then the limit law is going to hold, because you are dealing with the limit of the sequences. So, we can easily prove these things by yourself, but do not miss the point that both the series has to be convergent. So, now let us look at some other methods in which we can determine the convergence or divergence of a given series. So, one of the very powerful test is ratio test. So, ratio test, let a n I choose to be strictly positive numbers for all n. And given to us that if and let limit n goes to infinity a n plus 1 over a n, this is equal to L. This limit exists, limit of this ratio of two consecutive term a n plus 1 by a n, this exists and is equal to L. If L is strictly less than 1, then the infinite series converges. B, if L greater than 1, then diverges. C, if L is equal to 1, we cannot decide. Okay, so let us look at the proof of A, that is L is strictly less than 1. Therefore, 1 minus of L divided by 2 is strictly positive. Now, we take this to be our epsilon, right. Now, a limit of a n plus 1 by a n, this is equal to L. Therefore, for this epsilon there exists n sub naught such that mod of a n plus 1 by a n minus of L is less than 1 minus of L by 2 for all n greater or equal to n sub naught by the definition of limit. So, by triangle inequality, this is equal to, this will imply a n plus 1 by a n minus of is less than L plus 1 minus L by 2, because a n plus 1 by a n minus of L, this is less than 1 minus L by 2. So, which is equal to L by 2 plus 1 by 2, let me call this as a number q. Now, L is strictly less than 1. So, therefore, the first term is strictly less than 1 half plus half. So, that is 1. So, q is strictly less than 1. So, from this what do we get? This is true for all n greater or equal to n sub naught. Now, for n greater or equal to n sub naught, we have a n plus 1 is less than q times a n, right. Now, if you take the large n, so what we are getting? So, now a n naught plus let us say L, this is going to be less than q times a n naught plus L minus of 1, which is again less than q square a n naught plus L minus of 2. So, this is, if we go on like this, which would be less than q L a n naught. Now, to get the sequence of a n, this is essentially what we can do is that a n naught plus L, if we can show that this series converges, then this is going to converge. Towards this end, what do we see? That this side. So, now our series is we can write that a n naught plus n is lesser equal to q to the power n a n naught. Now, this series we are interested in summation over n. Look at the right hand side, q is strictly less than 1 and this is a real number which is not dependent on n. Therefore, this is going to be this side of the series, this is, if I take the summation over q to the power n a n naught, n equal to 1 to infinity, this is convergent, because this is a geometric series and q is strictly less than 1. Therefore, the series a n naught plus n is convergent, n equal to 1 to infinity is convergent. So, this will imply finitely many terms are there, 1 to infinity, a n is convergent. So, if L is strictly less than 1, then what we have shown is that this is a convergent series. Similarly, for B, if now L is strictly greater than 1, so now you choose your epsilon to be L minus 1 by 2, which is strictly bigger than 0. Therefore, mod of a n plus 1 by a n minus of L is less than epsilon for there exist n sub naught such that for all n greater or equal to n sub naught. Therefore, now this L minus a n plus 1 by a n is less than epsilon. So, what you have got, this is L minus of 1 by 2. So, L minus a n plus 1 by a n, this is less than L minus of 1 by 2. This implies that a n plus 1 by a n is greater than L by 2 plus 1 by 2, which is strictly bigger than, let us call this as some m, which is strictly greater than 1. This will imply that a n plus 1 is strictly greater than m of a n. Now, you go like this, because for large quantity. So, what you are going to get is that a n plus 1 is greater or equal to. So, in this process you will get a n naught plus n is greater than m to the power m a n naught. Now, m is greater than 1. So, this series diverges, that is m to the power n series diverges, because m is greater than 1. So, again by the comparison test, all of them are non-negative number and one a n's are greater than b n and b n is diverges, we will always say that a n is going to be divergent. So, now, for L equal to 1, we may not conclude, because consider series 1 over n, a n is equal to 1 over n, a n plus 1 by a n, this is equal to n by n plus 1, this goes to 1, but this series diverges, what we have seen earlier. Now, consider 1 by n square, this is equal to n square by n plus 1 square, this also converges to 1, but this is convergent. So, if L is equal to 1, we may not conclude anything. So, let us take few example of the ratio test. Look at what we have done this earlier. So, 1 by n factorial. So, therefore, a n plus 1 by a n, this is equal to n factorial by n plus 1 factorial, which is equal to 1 by n plus 1 factorial, and this goes to 0. So, this series is converges. This is example 1. Let us look at example 2. Suppose if you look at the summation over n square by n factorial, then a n plus 1 by a n, this is going to be n plus 1 square divided by n plus 1 factorial into n factorial by n square. So, this is 1 by n plus 1 into n plus 1 square by n square. So, which is equal to n plus 1 square by n plus 1 factorial. So, 1 by n plus 1. So, this is n plus 1 divided by n square, then this goes to 0, as n goes to infinity. Therefore, this series is a convergent series. Now, what about n to the power n by n factorial? Now, a n is equal to n to the power n by n factorial. So, a n plus 1 divided by a n, this is equal to n plus 1 to the power n plus 1 by n plus 1 factorial into n factorial divided by n to the power n. This is equal to, I can write this as n plus 1 to the power n into n plus 1 divided by n factorial, and n plus 1 is n plus 1 by 1 by n to the power n. So, this becomes n plus 1 to the power n by n to the power n, which is equal to 1 plus 1 by n to the power n, and this goes to E. We have seen, and E is greater than 1. Therefore, this series diverges, whereas n square by n factorial is convergent, but this series diverges. So, this is a very powerful to test the convergence. Another similar kind of thing is called the root test. Root test, it says that a n's are greater than non-negative number, and let a n to the power 1 over n, this exists, nth root of any non-negative number exists. This, and if we take the limit n goes to infinity, then this is, let assume that this is L. Similarly, if L is less than 1, then converges. If L is greater than 1, then a n diverges. If L is equal to 1, we cannot conclude. Okay, the proof is essentially similar in nature. So, we will just get the sketch of the proof. Now, what do you know? A n to the power 1 by n minus of L is less than epsilon. If L is less than 1, this is less than 1 minus of L by 2 for n greater or equal to n sub naught for some n sub net positive. So, therefore, what you have got, a n to the power 1 by n is less than L by 2 plus 1 by 2, which let me call it as q. This will imply that a n is less than q to the power n, and this q has to be strictly less than 1, because L is strictly less than 1. Now, use the comparison test. So, we know summation over q to the power n converges. So, as a result, a n's are non-negative, we have assumed. Therefore, by comparison test, summation over a n converges. Remember that here it is little abuse of notation. This is all after n sub naught. Again, there is an infinite series, and before there is a finite terms. Finite terms is not going to hamper anything towards it, they never contribute anything towards the convergence or the divergence of the series. Okay. So, now if L is greater than 1, exactly the same way as we have done it for the ratio test. So, you have to choose your epsilon cleverly. So, choose your epsilon to be L minus of 1 by 2. Therefore, what you get is that a n to the power 1 by n is greater than L plus 1 by 2, which is strictly bigger than one number. So, let us call it as m, m is strictly bigger than 1. So, a n is greater than m to the power n. Now, summation m to the power n diverges as m is strictly greater than 1. Thus, summation over a n diverges by comparison test. And you can think of C when L is equal to 1 by consider 1 by n. We know 1 by n to the power 1 by n, this goes to 1, but this series diverges. Now, if you take 1 by n square, then 1 by n to the power 2 by n, this also converges to 1. So, but this converges. So, what we have, we cannot conclude if L is equal to 1. So, some examples with the root test. Now, let us look at the series summation over n by n plus 1 whole to the power n square. This looks scary. So, let us see, a n is equal to n by n plus 1 to the power n square. So, a 1 by n divided by n. So, this is equal to n to the power n divided by n plus 1 to the power n, which is equal to 1 by n plus 1 to the power n by n to the power n, which is equal to 1 by 1 plus 1 by n to the power n. This converges to 1 by e, which is less than 1. Therefore, this series is convergent. Now, what happened to the series summation over n equal to, let us say 2 to infinity 1 by log n to the power n. Now, whether this series converges or the series diverges. Before that, let us just look at the series 1 by log n to the power square. Does this series converge? As a matter of fact, what we know is that log n square, this is less than square root of n. Therefore, 1 by log n square is greater than 1 by square root of n, which is a divergent, or you can see log n is less than 1 by square root of square, which is equal to 1 by n. This diverges, so this diverges. But what about this? Now, if we look at the root test, log n to the power n by n, which is equal to 1 by log n, which converges to 0. So, this series converges. Easily you can show that 1 by log n to the power any k, fixed k, that is a divergent series, but when you take 1 by log n to the power n, that becomes a convergent series. So, we will describe some more tests where we can determine whether the series is convergent or divergent again in the next lecture. Thank you.